So I wanted to show off this circular deviation plot that I developed in Excel. But before that, I've also talked about my position calculator, which will calculate true position of a hole based on its tolerance and its location relative to the datums. And it'll give you a nice little visual of exactly where the center point is in relation to the tolerance zone you have. And if you bring in an MMC example, you've got a circular tolerance zone, and now you can see you're still within tolerance with the position and the bonus tolerance you get. So this calculator's here, as well as a sine bar table, which will calculate your stack height based on whatever angle you're trying to get to, 10 degrees, 8 degrees, whatever. It'll tell you the stack height you need to build with the Joe blocks, as well as a total uncertainty ratio chart, which will help you pick your gauge based on the tolerance zone that you have, the size of the feature, the resolutions of the gauges, and the accuracy of the gauges. It's a nice little guideline to help you pick a gauge. But focusing back on the circular deviation plot, it was about 2 years ago, maybe. I was working on a project at work where I was using a CMM to measure a diameter, and you would get a typical output like this from a CMM, which has your measured average, your lower diameter, and your maximum diameter that was measured. But when this project, I really needed more than that, and I wanted to be able to export the data in Excel so I could manipulate it, make it look a little bit better. And one of the features that I wanted was to be able to basically zoom the data so that I could see kind of the shape of what's going on. So in this example, there's a pretty obvious sort of trilobe shape happening that you might not always get a great visual of. Sometimes the CMMs output, kind of a narrow band of your low and your high, and it can be hard to see the shape. But what's nice about this tool, we can scale it as much as we want to exaggerate that trilobe shape. So let's keep it at 20. The other feature I wanted is to answer the question is, are these in spec? So we have our nominal diameter, our minus, and our plus tolerance here, but from this plot, we don't know if all these points are in spec. So to do that, we can actually just bring in some more data. I'll bring in the nominal diameter, the lower spec limit, and the upper spec limit. And now we have these new circles. It's getting a little bit noisy and busy, so let's turn off our minimum and our maximum diameter plot and just concern ourselves with the spec limits. So upper spec limit in red, lower spec limit in orange, nominal here in blue, and then our data is still here in purple. You can see the average is a little bit above the nominal, but in tolerance. But actually some of these points on the outside are out of tolerance, and maybe even 1 or 2 points are outside of tolerance on the low end. Maybe we can zoom in a little bit more. It looks like this point is even just out of tolerance if we really exaggerate this plot. All right, so let's put it back at 20. So that can be useful if you're ever working on maybe a process capability and you're measuring your parts and you're trying to figure out what is your process capable of so you can set your limits. We can always just adjust these. Maybe we need to go to -7 and +7 to get a reasonable tolerance, and the plot will shift. We've still got a couple of points outside of tolerance on the high end, so maybe on the high end we need to go to 10. So this is a very basic example of process capability, but this can help you pick some tolerances that might be reasonable for your manufacturing process, or maybe this means your manufacturing process needs to get better. Maybe your process has complex steps involved, a lot of steps, turning, milling, heat treating, post-processing, whatever, and you want to track how this shape is changing throughout the processes. You can find the process that relaxes the material the most or deforms it the most. Theoretically, we could always plot even more layers of data. So this could be one layer of data. Maybe this is the second operation, but you could always put operation 3, operation 4. You could remeasure plot the data on top of each other and see how the shape is changing. But the tool's not set up for that right now, but possibility that could be done. Now, the way this tool works, let's clear the data, and we'll recreate our example. So you're going to enter a ½ inch or any diameter you want. You'll enter a minus tolerance and not -5, minus 0.005 and plus. And now we'll bring in, you need to drop in your coordinates in XY format. You can have up to 1,000 coordinates, but anything more than that, it won't be looked at. If your data is not already in XY format, you'll just need to convert it from radians and radius and angle to XY. So you can Google that, but if you're not sure, it's basically just radius times cosine theta, radius times sine theta. It's a pretty simple transformation, but the tool's set up to get exported in XY and dropped in. So I'm going to bring in some example data, drop it in here, and let's bring this back to 20. And as far as the minimum and the maximum scale factor, it's basically a formula that's based on your tolerances and your diameter. If you go outside the range, let's say we go to like 125, it won't stop you. It will plot something, but it won't be valid anymore. It'll give you a little warning here in red that you've gone outside of your zone, but other than that, just make sure you stay within the zone to get an accurate plot, and that just has to do with the way the plot shifts the points. I'll give you one more example. Let's say I've done all of this at a ½ inch, but it really will work at any diameter. So let's say we're going to go to 10 diameter with a -10 and a +10 tolerance. And now we have new minimum maximums, but I'm going to bring in some example data. So you see a little bit of the back end because I have this random generator here. And we'll drop that in. And okay, at 20, we don't see much. So we need to zoom in a little bit more. Let's go to 200. And now we're starting to see something. Let's go to 400. Oops, got a little bit shifted because of one of the points, but at any rate, this is pretty much just randomly generated noise, so it's not going to look very reasonable for a manufacturing process. But yeah, this tool works at whatever diameter you want to put in, however you can export your XY data and drop it in, put your tolerances in. So let's bring back our example. And finally, if you wanted to just export a nice little printout, you can click the export PDF and you will get a one-page summary of your plot. Your radius min, radius maximum are going to be based off of a 0, 0 coordinate and the smallest distance to one of your points and the largest distance to one of your points. The average diameter and the circularity are kind of estimations. This tool is more about plotting the shape than it is about giving you accurate diameters and circularities. It will be a good estimation, a nice little trend of your circularity issues, but it's not using 3 points as I note over here. It's really not using the 3 smallest points, the 3 largest points. It's just looking at the radius, the smallest radius and the largest radius. So good trend, but maybe not the same way a CMM would calculate things. Mostly just here to show the shape of the plot and let you play with the tolerances. So I hope you like it. Let me know if you have any questions.